Before we start the seminars, just a couple of quick announcements. I'll also remind you again at the end, we do have more sessions, seminars and meetings coming up over the course of this summer. So today, obviously, we've got our set of Solid Earth seminars. On July 31st, after another set of seminars, we have the CGU-wide AGM, Annual General Meeting. So please try to come along to that. We've got the virtual poster session on August the 6th, and then the CGU Solid Earth section annual general meeting will be held on August the 14th. So keep an eye out on your email inboxes because you'll be getting notifications about that from the CGU Secretariat. You can also find the information up on the CGU webpage and the Facebook page. A little bit of housekeeping for the seminars, just a reminder that because we're in webinar mode rather than standard Zoom mode, if you have a question for any of the speakers at the end of their presentation, please use the Q&A function rather than the chat function. And the way it'll work is that if you can type in your question to that Q&A function, I'll read it out and then the seminar speaker can answer. If we start going a long way over time, if there's a lot of questions, then I'll encourage you to type your questions in and then the seminar speaker can type their answers back to you later on during the session while the next seminar speaker is talking. Let me just check one thing. Okay, I think we're good to go now with the first of our seminars. So Mélanie, if you can unmute your microphone and start sharing your screen. Our first speaker for this afternoon is Mélanie Mathieu from UQAM, Université du Québec à Montréal, and she's going to present her work on anisotropy beneath Greenland.
So thanks, Fiona. Okay. No. Okay, so hi everyone. So thanks for the opportunity to present my work. So today I will talk about the interesting variation of seismic anisotropy across Greenland. So the Greenland is pretty much a stable continent and 80% of the island is covered by a thick ice cap up to 3 kilometers, which make the surface geology more difficult. Most of Greenland is made up of Precambrian rocks, and south of Greenland is mainly Archean craton, which is the North Atlantic craton, according to this map. So the major tectonic events are the formation of the Greenland. So in the Paleoproterozoic, it's represented by 3 major orogenic belts, which is the Inglophil Mobile Belt, Nax-Subtokidzean origin, and Ketilizian origin. In the east, we have the Caledonids, which is the continental collision between Laurentia, which Greenland was part of, and Baltica. And later in the north, we have some folding and thrusting. Also, Greenland is also the witness of the Hyson hotspot track, and this is it is pretty close to the Mid-Atlantic Ridge, always active at this day. So the goal of this research is to quantify the memory of the lithospheric mantle in order to know if major tectonic process can be preserved there. So, or this is the current mantle flow, or it is a combination of two or other sources. So we would investigate this question using the seismic anisotropy method in order to see the preferential direction of the minerals composing the mantle and make a comparison about the tectonics, geophysics, and geodynamics of the region. So the data I've used for the research come from 35 stations across Greenland, and they are earthquake of magnitude higher than 6 from an angular distance from a station about 80 and 150 degrees. So this is my sources, and this is my station, and they are from the IRIS and GeoFund database. So the seismic anisotropy, quick recap, this is the directional dependence of seismic wave speed related to structural fabrics and mineral alignment. And for the shear wave will separate into 2 orthogonal quasi wave propagating at two different speeds. So the fast one, the blue one here, will follow the mineral alignment and will be representing by phi, the direction of anisotropy. And the difference in the arrival time between the fast and the slow wave will be representing by delta t in the measurement. And this is the force of anisotropy and the thickness of the layer of the anisotropic media. So I chose the KS phase because of the polarization, radial polarization at the core mantle boundary. So the information between the sources and the core mantle boundary is erased after this polarization. So we just have the information at the receiver side. Also, this polarization erases the energy on the transverse component of the seismogram. So if there's energy, there's anisotropy. So to calculate this, we will try to find the best pair phi and delta t that will represent the energy on the transverse component. So we will use the method for minimizing the transverse component developed by Silver and Chan 1991. So we will start to find the best pair phi and delta t that after correction, the energy will be completely erased. The same thing for the motion particle. We will try to find the best pair phi and delta t that explain this motion. And after correction, the motion particle should be linear. So this is my results. So you can see that my blue bar are my excellent individual results. My green bar are my stacked results. My orange bar are some SKS measurement from other studies. And the black cross are my nodes. So you can already see that there's no clear pattern for all the island. So this is pretty variable. So you can see that for some stations close to each other, the direction is pretty much different. You can also see that my green bar, which is my stack, are not following, always following my individual measurements. It could be due to a high variability beneath the station, or probably more than one layer of anisotropy. So to confirm the presence of more than one layer of anisotropy, we look at the relation between the back azimuth of the seismic sources and the phi direction. So we try to look if there's a periodicity in my data, and if this periodicity is 90 degrees, because it is the clue for two-layer anisotropy. So this is three of my session with the best azimuth cover. You can see that my blue dot are my excellent value, and the null dot are my red dot are my null value. And you can see that there's a clear periodicity in my value. Look alike 90 degrees. So this is a clue that there's probably more than one layer of anisotropy beneath Greenland. I did the same thing for all the station to see if all the Greenland can be explained by two layer. And this is pretty clear that there's a periodicity in this graph. So we look forward and try to find a best model, two-layer model that will explain my data. So we use the MATLAB Toolbox MSAT by Walker and Wilkie 2012. So to do that, so we first try to model only the direction of the anisotropy of each layer with no dip, but the results was not as good as we wanted to. So I tried to add the dip of the layer in my model. So this is my results. It is pretty good visually, and the misfit between my model and my results are relatively low, about 5 to 10 degrees for each station. I did the same thing also for all the stations to say that probably more than just these three stations are explained by two layers, and they are probably dipping. So there's two principal sources for seismic anisotropy. There's the tectonics, frozen tectonics in the lithosphere, and the asthenospheric flow. So here is my principal results superimposed on the geologic map. You can see that for the station close to the orogenic belt, of the dashed line here, the anisotropy direction follow well the orogenic belt. And so if you look here and here and here, and if you look at the purple bar here, this is my shallower layer direction predicted by a 2-layer model. And this layer should be in the lithosphere in theory. So this should follow the tectonics. So if you look at two lake station, this is pretty good, and this is following this orogeny. But if you look at this station and this station, this is less clear. Also, I make a comparison with the astenospheric flow. So my prediction for the astenospheric flow come from 2 tomographic model and 4 viscosity model. Here I present only the tomographic model joined 2020 and 3 viscosity model, which I think fit more my results. If you first look at the green bar is the lower layer direction of anisotropy predicted by a 2-layer model. And you can see that for all the model, the layers followed relatively well my astenospheric flow. So this layer should be in the astenosphere. You can look at, especially in this part, that other stations are following the direction of the astenosphere, but these stations also follow the tectonics. So this is difficult to say which sources is the real one. And finally, I made some comparison with the Iceland hotspot track in the mid-Atlantic ridge. So this is the Iceland hotspot track proposed by Glisovic and Forte 2019. So from the 90 million years to 60 million years ago. So you can see that for the motion, for the tracks, for the station close to the tracks, they are following the sense of the track. But if we think about a hotspot, the hotspot could induce a radial current for some researchers. So the anisotropy should follow the radial. So probably that's explain why we see more than one direction for this station. But we couldn't say if this is really about the hotspot track. So for the mid-Atlantic ridge, in theory, it should follow. It should be perpendicular to the ridge because it's following the spreading rate of the ridge. But for the 2 stations closest to the ridge, like these 2 stations, they are perfectly parallel. You can say that this part of the ridge is faster than here, and this is always ultra slow rate of spreading. So probably that the formation of the ridge and cracking deuce are more higher to explain my data for this station than the spreading rate for that. But this station also following the astenospheric flow. So this is difficult to say which if the ridge have an influence on my data. So this is my principal conclusion. So the anisotropy beneath Greenland is highly variable. There's more than one layer of anisotropy, and the layers are probably dipping. The lower layer can be correlated to the astenospheric flows. The shallower layer can be correlated with the frozen anisotropy due to lithospheric fabric. The hotspot and the ridge could have an influence, but there's no clear evidence of that. And for further study, the measurement must be more able to discriminate the possible origin, because I can't say clearly what sources influence my data. So thank you.
Thank you very much, Mélanie. Are there any questions for Mélanie? If so, can you type them into the Q&A section, please? Here comes one. So here's a question from Phil McCausland. He says, what mechanism in the asthenosphere gives us anisotropy?
The current of the mantle, the current in the asthenosphere could induce some anisotropy in my minerals in the asthenosphere.
And are there any other questions? Okay, well, in that case, we'll say thank you very much again to Mélanie. And of course, if you do think of any other questions in the meantime, feel free to type them into the question and answer, and we'll try and get them answered for you. Okay, so our next speaker is Andres Peña Castro from McGill, and he's going to be talking about the seismicity sequence induced by hydraulic fracturing in Dawson Creek. So Andres, if you could unmute your microphone and share your screen for us.
Hello. Yeah, give me a second. Share screen. Can you see my screen now?
Yes, we can see it.
Yeah.
So
Okay.
over to you.
Yeah. Okay. Yeah, it's working, right? Yeah. Okay. Good. Good afternoon. So if you have more questions or comments about our research, you can also email me. So let's start. So I divide the talk in four parts. The first about why analyzing this earthquake sequence is important, or why is the motivation behind this study. The second part is related about how we observe earthquakes. The third part is the methodologies involved in the analysis of this earthquake sequence. Some of those methods include earthquake detection, earthquake location, and the development of numerical models. And the last part is a conceptual model that explains the earthquake sequence. So why is this important? So the figure on the right shows the earthquake locations in Western British Columbia and Eastern Alberta in Canada. Those earthquakes occur between 2009 and the end of 2018, and they are highlighted by the red colors. Additionally, here in the plot, it's also shown the in gray circles hydraulic fracturing wells. The inside on the right side figure shows the temporal correlation between the cumulative number of events or earthquakes events and the cumulative number of hydraulic fracturing wells. Now, out of those 20,000, almost 21,000 wells, only a small percentage correlates with earthquake activity. In fact, only less than 1% of those wells correlates with earthquake activity. Although it's a small number, these earthquake activities a nuisance for the nearby towns, and these different cities have been shaken by these events. Moreover, multiple earthquakes with magnitude 4 have been occurring in this area, while before 2005 there was basically no seismic activity. So for today's talk, I will focus on an event that happened in November in 2018 that has a magnitude of 4.2 that occurred in Fort St. John in British Columbia. So about our observations, we use a local seismic array deployed by McGill University, and also we use public stations. In the right map, the right figure, and show you a map of the locations. The in the blue diamonds, and they are scaled by volume. And you notice that close to some hydraulic fracturing wells, there is there are multiple events induced, while sometimes you see like close to hydraulic fracturing wells, there is no seismicity induced. If you want to know more about this, so with the data that I just we apply different earthquakes. The second was to obtain precise earthquake locations, and the last one was apply or explain the earthquake sequence using different numerical models. In the earthquake detection, we first use a classic STA-LTA method to detect events in this area. And second, we use a multi-station match filter approach that detects similar events which are based on cross-correlation. We use the Python parameter So here I put the number of events detected by each of those methods. So beforehand, the Natural Resource Canada in this box only detected 4 events, while the STLTA we detected 18 events, and with the multi-station match approach, we detected roughly 301 events. Here in the bottom, I'm showing you the temporal evolution on the seismicity. So here in red is showing you the cumulative number of detections, and in blue is the cumulative seismic moment. Here the largest jump in the cumulative seismic moment is generated by the main shock of 4.2, seismic moment 4.2, and the light gray and dark gray bars shows the amount of water injected per stage, and the timing between the first injection and the occurrence of the main shock is roughly 52 hours. Okay. Related to after we detect the earthquakes, we locate these events first using nonlinear location software that use phase arrival to locate events, and after that we use double difference algorithm. We use 2 double difference algorithms. The first one is Groklos and HypoDD. The main idea of this double difference algorithm is that if 2 events, the distance between 2 events is closer or smaller than the distance from those events to the stations, and you can remove heterogeneous structures in the velocity model that might not be included. So here I'm showing you, first I will talk about it. So we were able to locate 204 events that has these 4 phases. With the double difference algorithm, we were able to locate 59 events with Groklos and 68 events with HypoDD. With this double difference algorithm, the errors locations were reduced to tens. Roughly, the errors are tens to hundreds of meters. And here the right side, I'm showing you a map view of the relocated seismicity and cross sections of the seismicity. And you can notice that the seismicity distribution is similar regardless of which method you use for the relocation. And there are 2 main features that both of them highlight. So one of them is that there is a near vertical fault structure highlighted by the shallow seismicity. And the other one is the main shock was located at deeper layers, roughly at 4.5 kilometers depth. When we look together at the focal mechanisms for these different events, so we have a mixture of strike slip focal mechanism and also reverse thrusting mechanism for some events. For the main shock was a reverse thrusting, but the strike of one of the fault planes also agrees with the seismicity that we discussed before in the map. Okay. Now, we also build in-house, as a last step, we construct numerical models to understand this earthquake sequence. The first thing that we notice in here in the figure is that the injection happened at a depth of 2.2 kilometers, but the main shock happens at a deeper level of 4.5 kilometers. So how fluid injected can trigger these events? So there are different numerical models or mechanisms involved that we can use to explain this. The first one is pore elastic stress changes, and the second one will be pore pressure changes. In both cases, you reduce the stress in one case and meet the column failure criteria, or you increase the maximum and reduce the minimum compressive stress, and you meet the column failure criteria for those events. So we calculate the stress changes, including the ambient lithology and the injection history of the this well. And the figure shows that the column failure stress changes and also the figure on the right shows the pore pressure changes. For both cases, the stress changes are negligible or really small. So we have to come up with some hypotheses to say like how we can explain this phenomenon. And we first we hypothesized the existence of a highly permeable conduit that might have facilitated the fluid transfer from the injection to the main shock. So in order to do that, we embedded in a model two high permeability zones. One of them will be a vertical conduit, and the second one will be a damaged zone flanking the main shock fault plane with the fault orientation that we found from the focal mechanism. We perform different sensitivity tests using different permeability values typical of fault zones, and we also include different conduit thickness ranging from 30 meters to 200 meters. For all those tests, we calculate the change in the pore pressure. So here's the no conduit 10 to the minus 14, 10 to the minus 15, and 10 to the minus 12. When we consider a permeability of 10 to the minus 12 pore pressure increase, that one is the one that gives the highest, in this case 0.03 and 0.08 megapascal, which indicates that this is a plausible mechanism to explain the occurrence of this event. Oops. So the first step in this sequence of events was that the main shock was triggered by fluid diffusion or fast fluid diffusion into deeper levels. But then we wanted to see if the main shock inhibit or promote failure elsewhere. So in order to do that, we calculate column stress changes generated by the main shock or the static displacement of the main shock. So here I just show you a cross section of using the sleeve of the main shock and the locations of the aftershocks. So here in this plot, red means that in these regions, sleep is going to be promoted. And in the blue regions means that sleep is going to be inhibited or failure is not going to be, should not happen in this area. Most of the events are located in regions of failure. So the second step in this entire sequence is that the aftershocks are triggered by the static stress change of the deeper event. So here I'm just gonna show you the conclusions or the main points of our study that was published this week. So we developed numerical models to explain the induced earthquake by hydraulic fracturing in British Columbia. The first step in this sequence of events was that the main shock was triggered by rapid fluid pressure increase via hydraulic conduit from the injection points to a basement fault. And then most of the aftershocks are triggered by static column stress changes resulting from the main shock of seismic slip. And that's it. I will take questions now.
Thank you very much, Andres. Are there any questions? Last call for questions for Andres. Okay, well, thank you very much.
Okay, thanks.
Right, so our third speaker is Riddhi Dave from Université du Québec à Montréal, and she's going to be talking about shear wave velocity structure and seismic anisotropy beneath the Tanzanian, Wyoming, and North American cratons. So Riddhi, if you can unmute yourself, pop your camera on, and start your screen sharing, please. Oh, I've just seen two, hang on, I've just seen two questions come in for Andres. Andres, are you still there to answer some questions?
Yes, I'm here.
Okay, so the first question is from David Eaton.
Yes.
And he asks, did you consider aseismic slip as a possible stress transfer mechanism?
So we did not calculate exactly for a seismic slip, or we did not develop a method, but I know it's also a method a method that is also used to explain in certain cases induced seismicity. And it might be possible that a seismic slip happens in this area, but we don't know yet because it if you notice, there is like a little gap in seismicity in here. So we think that maybe while the foreshocks were happening, there was some induced seismic slip in the deeper layers also, but we didn't calculate any numerical models for that exact mechanism at least. So it's possible as well.
Great, thank you. And then the other question comes from Zara, who asks,
Yep.
have you considered the effect of stress shadowing to correlate earthquakes to the hydraulic fracture wells?
Stress shadow. I mean, like we only have like 1 or 2 events in the entire sequence located in the stress shadows. So yeah, like pretty much all the Earth seismicity is located in areas where you promote sleep. So yeah, I don't know if that answers the question.
Okay, thanks very much. Are there any last questions for Andres before we move on to the next speaker? Okay, it's all quiet, so I'd like to invite Riddhi Dave to start off her presentation, please.
Thank you, Fiona. I'm unable to start my video. It says, oh, okay, sorry.
There we go.
Okay. Okay. Just bear with me for a second. Okay. Oops, sorry. Hello and a very good afternoon to everyone. My name is Riddhi Dave, and the image here is actually not of any of the cratons that I'm going to talk about, but rather it's of Banff, and it's a way of me thanking you all for joining this session and listening to all of the talks during these very difficult times. So I'm going to talk about investigation and comparing of the shear wave velocity structure and seismic anisotropy beneath the Tanzanian craton, and then compare the results with Wyoming craton and the North American cratons. Now, I have long been interested in probing the evolution and modification of cratons, and the Tanzanian craton presented the rare opportunity to study the interaction of active rifting with stable cratonic lithosphere. Now, I have also modeled the Wyoming craton, which straddles the western edge of the North America craton along the Rocky Mountain front, and serves as an excellent specimen with the encroaching Yellowstone hotspot and the unique geotectonics of the area. So to kick off with the Tanzanian craton, here we have the tectonic and the geologic map of the craton. The study area forms the nucleus of the East African rift system, which bifurcates into the eastern and the western branches around the Archean craton. Now, the craton itself is surrounded by several Proterozoic mobile belts, such as the Ubendian belt, the Ozagaran belt, Kebaran belt, the Mozambique fold belt, and the Ruwenzori accretionary belt. The eastern branch of the rift system includes the Kenya rift, also known as the Gregory rift, which consists of several roughly north-south trending rift segments that widen into a 300-kilometer wide area of block faulting called the Tanzanian divergence zone. To the north of the craton lies the Uganda basement complex, which is a gneissic megmatitic complex. The western rift branch consists of various rifts, such as the Lake Albert Rift, Lake Edward Rift, Kivu Rift, and so on. Also, a very interesting feature here is the topography. The Tanzania craton has a mean elevation of about 1,200 meters, which is very uniquely high. So we have the images of the station locations, the event distributions, and the ray path density. And I'm not going to talk too much about the technique which I employed, other than the fact that I used two-plane wave method, which was developed by Forsyth and Lee to get Rayleigh and love wave phase velocities, which were subsequently inverted to get Rayleigh and love wave shear velocities. White's average and radial anisotropy, both separate and jointly inverted, were then calculated. The ray path density image here at 67 seconds illustrates a very good azimuthal coverage, especially within the Tanzania craton and the surrounding mobile belts and the rifts. So to take a look at the 3D Rayleigh and Love shear velocity structure in the upper mantle, on both the Rayleigh and the Love wave maps, we see the eastern and the western rift branches slower than the craton, and both the branches show variable structure in the upper 150 kilometers of the mantle, with the lowest velocities found beneath areas of Cenozoic volcanism. The fast velocities in this depth range extend to the north beneath the Uganda basement complex and to the east beneath the Tanzania divergence zone and the Mozambique belt, indicating that these regions together form a rigid block around which rifting has occurred within weaker mobile belt lithosphere. Now, at depths greater than 180 kilometers, a low velocity anomaly is present beneath the entire steady area that may well extend into the mantle transition zone. Now, these are the similarities between the two maps. As for the differences, these will manifest themselves in the form of radial anisotropy, which we will see in the next slides. So here we have the Voigt's average, which can be considered as an average of VSV and VSH in simplified terms. Below is the real anisotropy model of the region obtained by joint inversion of VSV and VSH. Now, on this slide, we are simply seeing how the models are changing along the north-south axis from west to east. And we will take a closer look at specific transects on the next slide. So I have 4 vertical transects trending west to east along a north-south axis for both Voigt's average and radial anisotropy. And the different features on these images are, we see that the craton is very well delineated on these transects. We also see the presence of cratonic-like lithosphere beneath the Uganda basement complex and the Tanzania divergence zone. As we saw on previous maps, most of the low velocity zones are constrained beneath the weaker rift systems and regions of young volcanism, with the lowest velocities beneath the Kenya rift dipping westward with a noticeable thinning of the cratonic lithosphere here. As for the radial anisotropy transects, we see emergence of quite a complex pattern of anisotropy in the region. The Archean craton, the Uganda basement complex, and the Tanzania divergence zone show negative anisotropy. Though this negative anisotropy doesn't really extend to the eastern edge of the Archean craton itself. The rift regions are associated primarily with positive anisotropy, except Kenya rift, where the lowest velocities are correlated with negative anisotropy. And finally, we see the emergence of a uniformly positive anisotropic fabric pervading the entire region below 180 kilometers. So through this schematic diagram, we're seeing the stratification of anisotropy beneath the region. And the theory of this study is that the large-scale, low-velocity structure beneath the entire East African plateau is actively pervading and exploiting the relatively weak lithosphere along the rift branches and manifesting in the form of negative anisotropy in the weakest rift regions associated with magmatic upwelling, wherein the example would be the Kenya rift. Now, anywhere else along the rift branches, the lateral strain from the plate motion is stronger than any upwelling induced strain, and thus we see a positively anisotropic fabric, such as beneath the Kivu rift. The westward dipping low velocity structure beneath the Kenya rift is also actively eroding the Archean cratonic lithosphere, as well as reworking the fossil anisotropy. Thus, we see a positively anisotropic signature on the eastern edge. The study very strongly supports the potential link between the pervasive mantle low velocity anomaly underlying the East African plateau and the theory of African superbloom. And this further explains the origin of the anomalous topography in this region, which possibly resides within deeper mantle. Next, let's take a look at the shear velocity structure and radial anisotropy beneath the Wyoming craton. Now, the modeling has been done using the same two-plane wave approach, thus rendering the comparisons quite reliable. Here I'm showing two vertical transects whose geographical location is shown on this map. On these shear velocity transects, we see relatively low velocities at all depths appear beneath the Yellowstone hotspot and the Cheyenne belt in the upper mantle. We also see a fast anomaly sandwiched between the hotspot and the Cheyenne belt. On the transect BB prime, we see that the rest of the craton is characterized by relatively high velocity, which is stronger above 125 kilometers. Also an interesting feature below 150 kilometers depth is this low velocity zone in the central eastern portion of our region. Now, comparing these features on the radial anisotropy maps in the upper mantle, we see that the strongest anisotropy is associated with the hotspot area, which can be interpreted as due to shear by the North American plate motion, since the viscous and since the weak and viscous upper mantle is more easily deformed. The low velocity anomaly in the central eastern craton beneath 125 kilometers correlates with the weakly positively anisotropic fabric of about 2 to 3%. And this can be again explained as a stronger shear deformation in weaker regions. The high velocity block between the hotspot and the Cheyenne belt corresponds to negative anisotropy, which grows distinctive with increasing depth and has been interpreted as a lithospheric drip, supporting the argument of mantle downwelling from small-scale convection. So these images reflect complex 3D small-scale mantle convection, which happened in 3 stages beneath the Wyoming craton that is actively modifying the remaining cratonic lithosphere. So the 3 stages are, the first stage would be a weakening due to hydration, which happened during the flat subduction of the Farallon slab, wherein the cratonic lithosphere was weakened. The second step would be the removal of the Farallon slab, which resulted in mantle upwelling and small-scale convection, which resulted in foundering of the deep cratonic root. And finally, the third stage is the small-scale convection, which is re-triggered and strengthened by the encroaching Yellowstone hotspot, and especially along the southeastern margin of the craton, which is continuously destroying the cratonic lithosphere. So now let's zoom out of the Wyoming craton and take a look at the bigger picture, which is the North America craton. Now, this craton is a mosaic of amalgamated Archean blocks and Proterozoic terrains, and it provides an excellent opportunity to investigate both extensively modified cratonic lithosphere, such as the Wyoming craton right here, as well as the relatively intact lithosphere of, say, the Superior craton. Looking at the shear wave velocity structure and the radial anisotropic structure of this region, we understand that with such a model, resolution of smaller features isn't really feasible, yet it provides important constraints on eroded versus intact keels. In the shear velocity images, we see that the lithospheric core is retracting towards the center of the continent with increasing depth. Now, the center here comprises primarily of Slave, Huron and Ray, and Western Superior cratons. In contrast, the Eastern Superior province and the Wyoming craton pretty much disappears at depths greater than 150 kilometers. Now, correlating this with radial anisotropy, the anisotropy is definitely weaker along the edges, and especially under the Wyoming craton, Archean Wyoming craton, indicating basal erosion. Also, the lithospheric root in the eastern part of the Archean Superior craton shows a weaker signature, which may have endured basal deformation and weakening induced by the passage of the Great Meteor hotspot track. So we can safely deduce that this indicates a connection between regions of weaker anisotropy in the lithosphere at the edges of individual cratons, suggesting the presence of asthenospheric upwellings, and 2, zones of pre-existing weaknesses in the continental lithosphere. Now, comparing these global results with more regional results helps in providing essential boundary conditions to erosion, modification, and eventual destruction of cratonic keels. So to summarize, the Tanzanian craton is actively being modified and eroded by the asthenospheric upwelling along the weaker regions. Also, the anomalous topography and the pervasive low velocities beneath the craton suggests a deeper mantle origin, such as the African superplume. The Wyoming craton has been actively modified and eroded by the small-scale convection, which was triggered in the past due to the flat subduction of the Farallon slab, and has been strengthened in the present due to the encroaching Yellowstone hotspot. And finally, comparison of these cratons with North America craton provides necessary constraints which play an essential role in understanding the processes responsible for modification and destruction of the cratonic keel. Thank you.
Thanks very much, Riddhi. I can see there's a question come into the box already, so.
Should I just stop the share?
That's fine, yeah. So the question is coming from Phil McCausland, and he says, nice talk. For the Tanzanian craton, is there any anisotropy from past possible plume events? A Lake Victoria plume, Kunene Kibaran Largignis province, at 1370 million years has been proposed, which would underlie and perhaps underplate Tanzanian craton in the Mesoproterozoic. Can this be distinguished from present-day sources of anisotropy?
Very interesting question. So the anisotropy results, there aren't too many studies which have been conducted in the Tanzanian craton, but there is anisotropy from shear wave splitting, which pretty much seems to indicate the general direction of anisotropy aligning with the plate motion. Other than that, anisotropy related to any kind of possible upwellings, especially from deeper mantle, has really not been delineated, really not been defined very well, possibly due to the restrictions that we have on the resolution. As for the Lake Victoria plume, do you know what depth we would be talking about at this point? Because I have not come across a possible plume beneath the Lake Victoria in the studies that I have seen so far, and neither do I see it on my models. Is it a much deeper plume, which is why we don't probably see it? It would have been a long time ago. So again, the thing is, so most studies seems to be aligning on this theory that much of the upper mantle, and even deeper below that, below the East African plateau, is sitting on this super plume, and most of the ancient fossil signatures and isotopic signatures would have been reworked due to this big source, this big plume source, and I have doubts that anything apart from the craton, where I do see some fossil signatures, anything apart from that in this region, I doubt we have any fossil. We have any way to distinguish between the present day sources of anisotropy versus the past, simply because the past is probably heavily reworked. I hope that answers the question.
Thanks a lot. Are there any other questions for Riddhi? I'll just give it a couple of seconds so people can type if they need to.
Sure.
Okay, it looks like there's no further questions, so thank you very much.
Thank you.
And then our next presenter is going to be Miles Bodmer from University of Oregon. And he's going to talk about subslab asthenospheric buoyancy and subduction dynamics, teleseismic tomography of the Cascadia subduction zone.
Hi, can you hear me?
You're just fine, yeah. So if you can start sharing your screen, then we'll be good to go.
Okay, hopefully that is working there. And it's not seeming to go forward. There we go. Okay, so thank you for having me today and letting me give this presentation. So I'd like to talk today about some work that I've been doing at the University of Oregon, looking at the Cascadia subduction zone, primarily using teleseismic tomography. And so what we're trying to do here is to figure out what the links are between the subslab asthenosphere, the subduction dynamics, and surface processes here, and understanding how these are all interrelated. So this is really going to be kind of an amalgamation of work that I have been involved in at the University of Oregon. So I won't have time to get into too much detail of any particular study, but I'd be happy to take questions after or continue discussing over email in the future. So jumping in, if this progresses forward. There we go. So why are we interested in Cascadia? So Cascadia is interesting because even though it's a relatively short subduction zone, it seems to be heavily segmented, both in its megathrust behavior and in the evolution of the forearc. So we think that we see three main segments in Cascadia, and these are a northern, central, and a southern section here, where the northern and the southern sections are typified by increases in plate locking, increased tremor density, higher topographies, and more rapid uplift rates. So when most studies try to understand what is happening in terms of segmentation, they tend to focus on properties of the overriding or the downgoing plates. But here we'd like to look a little bit deeper and try to understand if the oceanic asthenosphere has any role to play in this system. So as we move offshore and have denser seismic arrays that are sampling the offshore environment, something that we're discovering is that the oceanic mantle is much more heterogeneous than we would have previously thought. A result that highlights this is sort of a key result that I'll be presenting here. This is teleseismic P-wave tomography, averaged 100 to 250 kilometers depth. And we image these low velocity anomalies sitting beneath the subducting slab that are only present in the north and the south. So very much matching this segmentation pattern that we discussed earlier. And so in this talk, I'd like to put forward several different hypotheses for what we think is happening in Cascadia. So we think that the mantle dynamics here are such that there is variations in the physical state of the subslab asthenosphere here, and that these in fact are places where we have increased buoyancy in the north and in the south, and that these can modulate the subducting slab morphology and possibly things happening along the interface. And then we think that this in turn gives us a way to modulate and set up the conditions for segmentation, both in megathrust behavior and forearc evolution. And so if you don't take away anything else from this, what we'd like to emphasize here is that characterizing the oceanic mantle is really critical to understanding these subduction systems here in Cascadia, but very likely in other subduction systems globally. So let's look at this tomographic model a little bit more, what goes into it and how we can interpret these low velocity anomalies. So the data that we're using here primarily comes from the Cascadia Initiative array. This is over 350 broadband ocean bottom seismometers that are deployed over the span of 4 years, shown here as the green circles. So this is made to complement the existing seismic array, mostly coming from the US array, these inverted blue triangles here. And we'll be using both of these data sets in our tomographic imaging and just the offshore data set for some studies that I'm going to describe in just a second here. So one of the things for context that we'd like to know is, with this offshore data, what does mantle flow look like beneath the incoming oceanic plate? So we can start to explore this. This is a paper that we published in 2015. This is SKS splitting measurements beneath the Juan de Fuca plate system. And the big takeaway here is that there is a very big difference between splitting that is happening beneath most of the Juan de Fuca plate system here and what's happening down in southern Cascadia beneath the Gorda Deformation Zone. So in the north, what we see here is fast axis directions that seem to be subparallel to plate motion. And so the idea is that plate motion is driving viscous, it's driving flow via viscous coupling, and it's entraining mantle material into the subduction zone. When we look to the south, something very different seems to be happening. These fast axis directions are now subparallel to the Juan de Fuca Pacific relative motion direction. This is inconsistent with this entrainment model up to the north. And so what we think is happening here is that there's this mantle reorganization occurring beneath the Gorda, with the Pacific entraining material out to the northwest beneath the stagnating Gorda plate. So with this as a context, we can look back now at our seismic tomography and try to interpret these low velocity anomalies. We'll tackle them individually, first looking at the northern anomaly. So here we're looking at a slice at 150 kilometers depth and a profile that we've taken to be subparallel to plate motion and parallel to the SKS splitting direction, our inferred mantle flow direction. And so we're attributing this low velocity anomaly to the nearby Cobb hotspot, which is currently sitting at the Juan de Fuca Ridge, has a thermal anomaly of about 40 Kelvin. And if we look at this profile, what we see is that these low velocity anomalies actually connect back to the ridge where the Cobb hotspot is located. They increase in amplitude and they get shallower as they approach the subslab region here. And so the idea is that hotspot material is able to find its way onto the Juan de Fuca side of this system. It gets entrained into northern Cascadia. As it does so, it upwells, undergoes decompression melting, and then finally sits in the northern part of the subslab. If we look down in the south, we have a slightly a different story. Here, again, we're taking a profile that looks along the fast axis direction for anisotropy, so our inferred mantle flow direction. We see low velocity anomalies in the subslab that now connect to the west to these shallow low velocities beneath the Gorda. And so the idea here is that this low velocity anomaly is due to the plate fragmentation processes of the Gorda offshore. The Gorda is this diffuse plate boundary that is internally deforming because of the interaction between the Pacific and the Juan de Fuca plate. It's stagnating in a hotspot reference. And as we mentioned from the shear wave splitting, what we think is happening is there's this mantle reorganization happening beneath there. And so the idea here is that the Pacific is entraining material out to the northwest, and that material gets sourced from beneath the Gorda Deformation Zone and in the subslab region of southern Cascadia. It promotes a region of upwelling. That upwelling region undergoes decompression melting, and that gives rise to these low velocities that we image here. So both of these low velocities we have inferred to be some combination of partial melt, possibly increased temperatures, and that's going to give rise to increases in buoyancy in the subslab. So that is what we've tried to estimate here on the right-hand side. So this red curve here is if we take this entire low velocity anomaly and try to explain it just with the presence of partial melt. And if we allow temperature to play some role, that's going to actually increase the amount of buoyancy we have. So we've allowed that to come in bins of 10 Kelvin here, shown as the gray contours. The takeaway from this is that we have on the order of a few megapascal increase in buoyancy in the subslab region in the north and in the south. And so this is really interesting because it is correlated with a lot of observations that we have in Cascadia. So these subslab anomalies are co-located with places where we see increased plate locking, shallower slab dip angles, higher forearc topographies, increases in uplift rates, erosion rates, subsidence, and increases in tremor density. And so we think we can put a model together that will link these observations through a common system. And so what we're suggesting here is that these subslab buoyant anomalies are able to modify the subducting slab in some combination of changing slab morphology or changing the nature of plate coupling along the interface. This in turn is going to influence where we see segmentation both in the megathrust behavior and in the evolution of the forearc here. So we can take a look at this in a little bit more detail here. So again, I've plotted up our subslab buoyancy profile here. And if we think about these buoyant anomalies sitting beneath the subducting slab, one of the first things we can think that it might affect is the actual morphology of the slab. And there seems to be some evidence for this. We can look at average slab dip angle in the upper 30 kilometers, and we see that we have shallower slab dip angles in northern and southern Cascadia compared to central Cascadia. The next thing that we can think about is that this might be influencing the nature of plate coupling along the interface. And there seems to be some evidence for this as well. We can look at plate locking inferred from geodetic measurements and see an increase in plate locking in the north and in the south. So this is really interesting because if these things are modulating along strike, they should have implications for the total forces along the interface and implications for the forearc. And we can look at this by looking at this simple model of the forearc, where here we're just looking at a force balance between the forces that would promote gravitational collapse of this forearc wedge and the total resistive shear forces along the interface here, F naught. So one of the things that we can see here is that F naught can be increased in one of two ways. The first is by increasing W, the coupled width, which is sensitive to the dip of the interface. And the other is by increasing the amount of plate coupling. So in Cascadia, it's been shown that F naught is roughly equal to F. So this has implications for what's happening in the forearc itself. And this is sort of twofold. The first is that if we increase F naught locally, we should be increasing the amount of forearc topography that we can support via these lateral shear forces, this term B here. And the other is that if uplift here is due to unrecovered strain during the seismic cycle, then an increase in F naught might help us to understand where we're most likely to build up topography in the long term. So we can look at some data from Cascadia, and there seems to be some decent evidence for this occurring here. First, we can look at a elevation profile of the forearc, and we see that we do in fact have elevated topographies in the north and in the south, where we have our subslab buoyancy anomalies. We can now look at things like uplift rates on over many different timescales. First, looking at the timescale of a single seismic cycle, we see that there is larger uplift rates in the north and in the south. Here we've plotted as these dots here, GPS measurements. The average is shown here as this black line. There's also an increase in coseismic subsidence in the north and in the south. This is a very similar pattern to what we see in terms of long-term rates, where we have increases in erosion rate estimates in the north and in the south, and long-term uplift rate estimates in the north and in the south. So to put all of this together, what we're suggesting here is that we have these low velocity anomalies that we have imaged in the subslab region. They're only present in northern and southern Cascadia. And using our mantle flow information as context, we've interpreted these to be localized upwellings where there is partial melt present. That gives rise to increases in buoyancy in the subslab region. We think that that subslab buoyant anomaly can influence the subducting slab either by changing slab morphology, shallowing slab dip angles, or by changing the nature of plate coupling. If either one of those things is happening, that should have implications for the total resistive shear force along the interface, and that in turn has implications for what's happening within the forearc. These are twofold. So the first thing is that if topography is being built up through unrecovered strain during the seismic cycle, which there is some evidence for because the inner seismic uplift rates are very similar to those of the long-term uplift rates, then localized increases in F naught mean that our subslab buoyancy could be indirectly influencing where we're most likely to build up topography in the long term. And then the other thing is that our subslab buoyant anomalies then give us a way to explain how we can support topography in the fork. So regardless of how topography gets there, it needs to be supported somehow. And this gives a way to say that changes in these total resistive shear forces can support these variations in topography through these lateral forces here. And so I'm probably running a bit over my time, so I'll throw up the conclusions here, and I'd be happy to take a question or two. Thank you very much.
All right, thanks very much, Miles. Are there any questions? And again, we'll give it a couple of minutes for people to type in their questions.
Sure.
Okay, the questions are now coming in thick and fast. So we have a comment from David Eaton saying very nice presentation. So thank you for that, Dave. The next question comes from Sam Butler, and he asks, do the nature of tremors also correlate with the difference in subslab buoyancy?
They do. So I didn't show this in detail. It quickly went by in the beginning. But if you take a look at just a map of tremor density, you have a very similar pattern to where we see our subslab buoyancies. Linking those two together is a little bit trickier. They are correlated spatially, and the tremor seems to be at sort of the eastern edge of where we image these low velocity zones, but there definitely is a correlation there.
Okay, thank you. And then we have a question from Phil McCausland, and he asks, is the Juan de Fuca oceanic lithosphere any different near the Cobb hotspot versus other parts of the spreading ridge north to south?
Yeah, I believe there's some work done there, geochemical work that shows variations. I believe there's some gravity work that shows some variations there as well, but there's sort of a decent signal to see where the Cobb hotspot is. And it's actually a little bit, it's slightly removed from where you would think that it might be based on just the bathymetry too. So there's a slight disconnect there. And so we've connected it down to where we see these sort of deeper anomalies, and we think the Cobb hotspot is.
Great, thanks very much. Are there any more questions? All right, I think you're off the hook. Thank you very much.
Thank you very much for having me.
And then so we can come to our final speaker for this afternoon. So we have Robert Shcherbakov from University of Western Ontario, who's going to talk about the statistics and forecasting of aftershocks during the 2019 Ridgecrest, California earthquake sequence.
Hello everyone, and good afternoon, and good to join you all. So let's all share my screen first. Do you have that? Do you see my screen right now?
Yes, we do. Thanks.
Okay, yeah. Okay, so today I'm going to talk about statistics and forecasting of aftershocks during 2019 Ridgecrest, California sequence. So here's a brief outline of my talk. So I'm going to present this problem in a little bit more general problem of computing the probabilities for the magnitudes of the largest expected earthquakes to occur during particular sequence. It could be aftershock sequence or general earthquake sequence. And typically here we can employ two approaches, and one is based on the extreme value distribution, and the other one uses this Bayesian approach and tries to compute this Bayesian predictive distribution. And I'm going to introduce briefly those approaches, and particularly I'm going to apply that for that 2019 Ridgecrest California earthquake sequence and try to compute basically the probabilities for the occurrence of those events. Here's the map of the 2019 Ridgecrest California earthquake sequence. And so here, so switch to sequence started with a really strong earthquake of magnitude 6.4. Here's just the focal mechanism of that event, which occurred on July 4th, slightly more than a year ago. And then approximately 1.4 days after that, 7.1 event occurred. And in red, those solid boxes, I illustrate the aftershocks which were generated by the 6.4 event, and blue circles, they indicate the aftershocks of 7.1 event, and all these colored events are above magnitude 3.2, and the rest of the events are below that threshold. So here's now the approach. So that means if we have some sequence of events and we say can observe that sequence, and we call that training sequence, say starting from T0 to T end. And then we want to use that information, say the times and magnitudes of those events, and we want to forecast, basically compute the probabilities for the occurrence of the largest events during some forecasting time interval. And so that forecasting time interval could be 1 day, 7 days, 5 days, or 10 days, or even a month. And we also can collect that data over some time interval, say it could be 2 days, 3 days, it depends on particular sequence. And sometimes it's important, like say if we have a strong event and then we want to compute the probabilities for the occurrence of the strongest aftershocks after that event. Or in this particular case of the Ridgecrest sequence, we had a relatively strong event before the main shock. And so if we can use that information and what we can tell about the occurrence of that main shock. So as I mentioned, typically we can employ these two approaches to compute those probabilities. And one is based on extreme value theory, and that was typically is used nowadays, say to compute those probabilities for the occurrence of the expected largest events. And this is based on this Rosenberg and Jones work using the extreme value theory. And more recently, we developed a little bit more advanced method, which uses the Bayesian sort of approach and also Markov chain Monte Carlo sampling of the posterior distribution to compute this Bayesian predictive distribution. And then that Bayesian predictive distribution allows us to compute those probabilities for the occurrence of those events. And that was published last year in Nature Communications. So first of all, we also have to define the earthquake rate model. So it means we want to specify how earthquakes are evolving in time. And most commonly used model, it's a Amori-Utsu model, or simply modified Amori law, which states that, say, the rate of the occurrence of the earthquakes, which is, say, number of events per unit time occurring after the main shock, decays with time according to this relatively simple formula. It's also possible to use a little bit more complicated so-called compound Amori law, where if we have two strong events and that event can generate its own aftershock sequence, so that means the total now the rate is going to be like a superposition of those aftershock sequences. And in this case of the Ridgecrest event, we had a strong foreshock which generated its own aftershock sequence, and then later we had the occurrence of the main shock. So that means we can employ this compound Amori model to describe that type of evolution of the sequence. And in this case, in compound Amori law, tau m means the time of the occurrence of the main shock, and this is the Heaviside step function. So it means the second term, it corresponds to the aftershocks generated by that strong 7.1 main shock, and the first term applies to the sequence generated by the first, that 6.4 foreshock. And also, we have a little bit even more sophisticated model, and this called epidemic type aftershock sequence model, which was developed by Agata in 80s. So that model assumes that now the total rate of the occurrence of earthquakes is a contribution from all earthquakes which are occurring in the past. And so it means that now it's a superposition of those Amori type kernels, and that defines this ability of earthquakes to trigger subsequent events. Now, finally, also we want to specify the how the magnitudes are distributed, and typically we use this left truncated exponential distribution, and in statistical seismology it's more known as Gutenberg scaling, and the b-value is related to that beta through this simple relationship. Okay, so now let's briefly, I'll mention about the extreme value distribution. So that means this was developed by Rosenberg and Jones, and then also we clarify that a little bit more in our work. So this model gives basically the distribution for the occurrence of the expected largest events in the sequence above certain magnitude, and that model depends on the rate, and basically this is the productivity, which is the integration of the rate during that forecasting time interval, and also on the frequency magnitude statistics. And of course, to compute now the probability for the occurrence of the earthquakes during some forecasting time interval, say this delta t, we need to specify the model parameters. But of course, we don't know true model parameters. And in most cases, we do point estimates, say from using the maximum likelihood method or some other methods. We estimate, say, parameters of the decay rates or just the parameters of the frequency magnitude statistics. And then we plug those numbers, and this will allow us to compute the those probabilities. So now we also developed a little bit more sophisticated method, and based on the Bayesian analysis, and this is called Bayesian predictive distribution. So that means we can compute now the so-called Bayesian predictive distribution, and this allows us to incorporate all the uncertainties associated with the model parameters. Basically here, I'm integrating over all uncertainties associated with the model parameters. So it means I'm not taking simply the point estimates for each parameter of the rate model or the frequency magnitude statistics, but I'm integrating over all those uncertainties. And those uncertainties of the model parameters are obtained from the posterior distribution function. Okay, so now I'll show you the application of those methods to this particular 2019 Ridgecrest earthquake sequence. So here's now one particular example of computation of the Bayesian predictive distribution and extreme value distribution for that particular sequence. So red curve and the dashed blue curve, that gives the case when I include the foreshocks into the analysis. And the other two, that's cyan dashed dot line and short dashed curve, that gives only the use of the aftershocks of the 7.1 event. And forecasting is done during the 7 days, and that is also, if we're using the foreshocks and aftershocks, we're using only 1 day of aftershocks after 7.1 event. And of course, now if you're using the Bayesian predictive distribution with the ETAS model, this is that red curve, and dashed curve, it's an extreme value distribution with the compound Amori law. And from this analysis, we can see that, say, if we pick if we're expecting to have, say, earthquake of magnitude 6.1 during the next 7 days, if we include the foreshocks into analysis, that gives us a higher probability. So it means that indicates that we observe higher probabilities or forecast higher probabilities for the occurrence, say, of those events if we include the foreshock sequence as well. So here's now the evolution of the sequence, and here I'm showing the computation of those probabilities for those extreme events above magnitude, say 4.5, 5, 6.1, 6.4, and 7.1. And I'm computing those probabilities as the sequence is progressing. Say after 1 day, so those numbers gives the probabilities of the occurrence of events above, say, 7.1, 6.4, 6.1, 5, and 4.5 during the next 7 days. And say then, if we're approaching this 2 days after the main shock, that's 7.1, we can compute those probabilities again into the future during the next 7 days, and so forth. And then so that gives us now the evolution of those probabilities in time using this Bayesian predictive distribution. For illustration, I also show the actual occurrence of the earthquakes during that evolution of the sequence, and that red curve gives the fit of the ETAS model, which basically describes the rate of the occurrence of events using the ETAS model. Here's now the comparison of those combination of these different methods and different model rates. And so using the Bayesian predictive distribution with the task model, or using the Bayesian predictive distribution and only Amori-Utsu law, or using the extreme value distribution with the Amori rate, or extreme value distribution with the compound Amori law. And it's the main sort of takeaway from this graph is just showing that inclusion of the four-stroke sequence, say in case of the Bayesian predictive distribution with the task model or the compound rate, it gives larger probabilities for the occurrence of the events during the evolution of the sequence. And this is for events above magnitude 6.1 during that sequence. Okay, so that's we be able sort of to compute those probabilities, but now it's important to see how well, or just how to verify basically the those forecasts. Now, to do that in the work which is now under review, I applied several methods, and one of them, we can simply see how we can forecast, say, simply the number of earthquakes above certain magnitude. And on this graph, I'm showing those black solid diamonds, actual number of earthquakes at the end of each forecasting time interval. Say this first point gives us that actually 86 events above magnitude 3.2 occurred after 1 week after the 7.1 event. And so that black solid, those diamonds indicate actual number of earthquakes at the end of each forecasting time interval. And now I'm also showing now the forecast based on those three rate models, so using the Amori-Utsu model, or compound Amori law, or ETAS model. And it's also showing those bands, those gray, the colored bands, shaded bands show the spread of those numbers based on those rate models. And it's turned out that, say, the Amori-Utsu law in most cases underpredicts the number of earthquakes above magnitude 3.2 for that particular sequence. And it's turned out that the ETAS model performs the best in this case. And in the work, I also present some statistical tests which also confirms that the ETAS model is the best in this respect. I also did this computation of the so-called sample information gain, which gives us, or compares basically two models based on their likelihoods during the forecasting time intervals, and selects which model performs better. And again, comparing, say, simple Amori-Utsu model versus the ETAS model, or compound Amori-Utsu model versus ETAS model. In both cases, the ETAS model basically performs better in terms of the forecasting of those sequences, of that particular sequence, and computing the probabilities for the occurrence of those events. Okay, in conclusion, so that 2019 Ridgecrest earthquake sequence was characterized by the complex clustering of seismicity, with earthquakes occurring on a distributed fault network. And I use these two approaches to compute the probabilities of having the largest expected earthquake to be above certain magnitudes and during the fixed forecasting time intervals during the evolution of that sequence. And the results indicate that incorporation of that four-stroke sequence and the ETAS model was critical to compute those probabilities. Thank you.
Thank you very much. Are there questions about this talk? While we're waiting to see if people are typing in their questions, I'll just do a quick reminder for everybody that we have a number of upcoming CGU events, notably the CGU-wide annual general meeting coming up next Friday, July 31st, the CGU virtual poster session on Thursday, August 6th, and then the Solid Earth section annual general meeting is coming up on Friday, August 14th. So I'd encourage everybody to attend those sessions. So are there any questions? Okay, well, it looks like there are no questions. So I'll thank you very much once again. And thank you to all of the speakers for their talks this afternoon. And that concludes our session.